Again, my name is Joanne Lowe, and this is Cesar Torres. We're from UC Berkeley, and we're happy to present to you today aesthetic electronics, designing, sketching, and fabricating circuits through digital exploration. This is a very fun collaborative project between UC Berkeley and Adobe. So in today's presentation, we're going to present the vision of aesthetic electronics. Aesthetic electronics is the vision where the functional circuits, the physical forms of functional circuits, can embed themselves in art form. For example, electrical traces, capacitive buttons, and optical displays can all be really beautiful art. But in today's presentation, we're going to focus on a subset of aesthetic electronics, which is aesthetic circuits. Aesthetic circuits is our definition of the form of electrical traces can take on a myriad of different visual design possibilities. So we're going to talk about the value of aesthetic circuits, the design difficulties that users encounter when designing with them, mainly balancing electrical functions as well as aesthetic values. And then we're going to present to you our digital design tool, which is called Ellustrate. Is designed to help users to design, fabricate, and debug these aesthetic circuits. So aesthetic circuits can actually be found in a lot of arts and design forms, but they can actually make a lot of practical sense as well. For example, we can think about how to incorporate electrical functionalities into the aesthetic design of electronic devices. And that opens up a lot of different possibilities in where we can plate these electronic devices. One of the examples is by having capacitive buttons and LED display that look like temporary tattoo. They can go on the user's skin and move with the user's skins and go wherever they are. Additionally, we can have fabric with conductive cores, and they can potentially change with heat and display information on a piece of fabric, as well as detect gesture with capacitive sensing on fabric. So as awesome as aesthetic circuits are, there are a lot of design difficulties associated with them. For example, you can imagine a lot of us are engineers and designers here. If you need to design electronic devices, thinking about both electronic functions and aesthetic values, the problem becomes extremely difficult. Additionally, aesthetic circuits by themselves are actually a lot of times enabled by different non-traditional conductive materials, such as graphite ink, conductive thread, and copper tape. So all these materials have a lot of interesting electrical and visual properties that we can leverage to create many different things. However, there are a lot of electrical functions that are not visible to users. For example, graphite ink can be up to 50 times more resistive compared to copper tape, and conductive thread can go all the way up to 400 times more resistive compared to copper tape. These are things that are not visible to user, and they can be kind of hard to deal with unless the user is explicitly told how to debug them with a multimeter. So on top of all the design difficulties, fabrication can be very tricky as well. So we talked about all the different materials and fabrication processes. You can imagine all of them have their own little quirks and unique properties that users need to deal with. And so hardware debugging and material debugging so far has been something that people need to learn from in in-person setting, mostly from people who are more experienced in the area. All these things that I mentioned before are great barriers to broader participation in designing aesthetic circuits. And so there are some digital tools out there to help users to explore hardware design in the digital realm. Paulos is a very great example. It's a digital program where a user can design microcontroller circuits within a digital design tool, and the tool actually helps you to fabricate the circuit at the end. To go a little more traditional circuit design route, we have 123D Circuits and Circuit Scribe, and also Eagle. They help users to design the circuit, have a lot more electronic functionality, but not so much the fabrication side of help. All of these tools tend to stick with very straight line circuit aesthetics, but not so much the shapes and the different drawing capability that we hope to offer. Additionally, they don't offer any fabrication, or with the exception of paper pulls, actually. They don't offer a lot of fabrication help, and all these tools do not help users to debug their circuit once they're done with fabricating the circuits. And that's the gap that we think that Illustrate could really come into play. So in today's presentation, we are going to, actually that's interesting. Okay, so going back. To fill the gap of all the problems that we have talked about before and the digital tools that were presented, we really wanted to create a tool that allows users to foreground circuit design as a site for creativity. And so we created a tool that will allow users to sketch their design, fabricate, and debug their design. We specifically designed this tool for circuit novices who might be more experienced in visual design, but are less experienced in circuit design. And to that end, we also limit the electrical function scope of the tool such that user can focus on creating simple LED circuits that really demonstrate and foregrounds simple electrical rules. So in the system architecture, you can see that a user can sketch the circuit within what we run Illustrate on an iPad Pro, so they can have a very natural interaction on the iPad Pro. And then the the tool actually validates whether the circuit is well connected and if there's any electrical violation. After we make sure the circuit is connected well, the user can print out the paper template and start drawing on it and fabricating the circuit using the fabrication and debug guide provided by the tool. So with that, I'm going to pass it on to Cesar.
Thank you, Joanne. So I'm going to talk a little bit more about the system architecture and some of the unique challenges of this particular domain. So Illustrate was built as a web application, and it runs on a pen and tablet interface. The application is decomposed to these sections. Specifically, we have a design phase where we expose a traditional canvas sketching interface. This interface produces a graph structure that allows us to provide some useful feedback to users. Let's take a look at what this looks like. Here we see the ability to drag and drop vector graphics onto the canvas. These graphics are annotated with electrical information directly into their SVG representation. This allows us flexibility of specifying custom footprints for a variety of components, including surface mounts and custom breakout boards. From this little bit of electrical information, we encode electrically positive areas as red and negative areas as black. Here we see a user drawing strokes which inherit the polarity of intersecting elements. We provide a simple modal dialog if a user ever introduces an electrical short into the design, and the model highlights and removes the offending element, ensuring that the circuit is electrically valid. However, it doesn't have to be the case that we need to always be fully cognizant of electrical rules. In this freehand drawing, traces are electrically neutral and colored in gray. Once a user decides to introduce a power source into the design, we can see how polarity is propagated to these visual elements. Lastly, the circuit sketching domain has a widely expanding set of materials. We provide a palette of the most common materials, including silver ink, copper tape, conductive thread, and graphite paint. We compute the resistance of each of these material. We compute the resistance of each material trace based on the model of sheet resistance, and more details are in the paper as to how we implemented this. So let's take a look at an example of a circuit sketch. So here we have 3 LEDs connected in parallel in this ladder representation. From this sketch, we extract a graph structure that allows us to extract some useful information for users. We see rendered in purple electrically important traces and rendered in gray visual traces. This is particularly useful for parsing complex graphics. By traversing the graph and gathering edge lengths, we can provide users a bill of materials as well as some common checks, ensuring that all components have connections present. So what happens when we break a circuit? So here we have removed the grounding path for each LED. Our validation step alerts the user of issues with the circuit and highlights all the problem elements. Once Sketch has passed validation, we provide a fabrication and debugging guide to aid users with realizing their circuits. So revisiting this latter example, there are a couple of ways that we can fabricate the circuit. One is to draw all the silver ink traces first and then lay down components. However, through interviews with expert circuit educators, we found that best practices follows a modular decomposition of the circuit. Using that same graph structure as before, we find all unique paths from power to ground. And this allows us to guide the user to incrementally construct their circuit. For LED circuits, this means first laying out a battery source and ensuring that the proper voltage is being received from the battery. And then, for each branch, it means first drawing the trace. In the case of silver ink, we introduce an additional drying step and integrate a timer widget. Once the traces have dried, the user is guided to verify that each trace has the proper resistance before laying out the LED and verifying this substep. This incremental development ensures an easier to debug circuit. And so this simulates how a user might construct the circuit. And it also provides motivations to users to complete their design. So here we have 2 LEDs and 3 more to go. As you just saw, we provide resistance checks based on modeled resistance value from the drawing, and we indicate to users where to place probes. Debugging assistance is available for each step and provides users information on best strategies for debugging circuits. This allows us some flexibility to indicate debugging instructions that are material specific, such as how to handle resistance issues with silver ink and copper tape. In the end, this design tool allows us some extra degrees of freedom for designing circuits for papers, textiles, and interactive objects. In order to understand how this translates to users, Joanne is going to tell us a little bit more about our user evaluation.
All right. So we got this tool, and we recruited 10 participants to join us to user test this tool. Again, all these users have experience in visual design, but not so much circuit design. And they were given the task of designing aesthetic circuits with 5 GPtronic LED tickers, a battery, and a silver pen to draw the traces. They were asked to design their circuits on an iPad Pro running Illustrate for the first 20 minutes. And after the tool validates that it's actually making a valid circuit, well, then they can fabricate and debug the circuit using the next 40 minutes with the fabrication guide and the debug guide provided by the tool itself. So these are some examples of circuits that are designed by our users, and we did a visual semiotic analysis and found that there are 4 patterns. One is functional, mimetic, constructive, and symbolic. We want to talk about the symbolic design a little bit more. So in the symbolic design, some users actually start telling a story using electrical traces rather than just using them to connect different components and using them as artwork. In this particular example, the user said that the birds were yin and yang, and the electrical traces were actually drawing the power to the light at the end. This is some the level of creativity demonstrated by our users is very encouraging to us in future work. Another very interesting thing that we have noticed is that other users have all used the tool and they were all successful in creating their design. Some of them were actually thinking that the design tool will be more indispensable to them in the future compared to the fabrication portion. In fact, a lot of them think that they can grow out of the fabrication portion of the tool. They wanted to find the rationale behind each recommendations so that they can fabricate these circuits without the fabrication portion. One example is that they were impatient in waiting for the ink to dry, and so they start to observe the wet and dry ink color on the paper so that they don't need to wait for the timer to go off, and they can just look at the color and move on. So we found that this kind of level of wanting to understand more is also very encouraging to us in our education angle as well. Another interesting observation that we have made is the transference between the digital and physical model of the circuit representation. So like I said before, a lot of these electrical properties were actually invisible to users before and were revealed to them in our digital design tool using different color representations. And users actually memorize that color representation within the digital tool and bring with them to the fabrication design or fabrication step. So in this particular case, the user actually memorized the different traces of red and black, and they said, I know the red and black are not supposed to cross here, although they are just using silver ink to draw all their traces. So we imagine that in the future, we'll be able to incorporate more complex electrical model, such as the water flow model, to explain current design or current flow within the wire. So again, Ellustrate is situated with the bigger, broader set of work that we like to do in the aesthetic circuits, and we would like to bring some features into Ellustrate to further this work. First of all, Ellustrate is built on a web platform, and so we now imagine it to be perfect to use it to establish an online community where people can share their designs and share their tips and tricks in fabricating their designs. We imagine this to be very useful for other circuit educators to use in their own setting. Additionally, we want to push the envelope of integrating aesthetic and electronic functions. For example, we want to incorporate more complex electrical simulations within the tool, such as impedance, capacitance, and change in resistance while moving the resistor. And we want to explore this function called auto-aesthetic routing, where users can combine the different aesthetic values with the aforementioned electrical functions and tune the different balance within the tool and explore the different balance themselves. So today we have presented to you Illustrate, which is the tool, again, we situated within our vision of aesthetic electronics. Aesthetic electronics is what we imagine functional electronics to be, where it's a combination of a deep understanding of scientific principles and appreciation of the arts. Our work is very much motivated by lines of research where advanced technology is actually enabled by the exploration of materials in the artistic realm. And we believe that to get to that vision and see aesthetic electronics being in forms and functions that we can't even imagine today needs to be started with education. And that's why we created Illustrate. So last but not least, we would like to acknowledge our user study participants, all the experts that have helped us, especially SIGCHI and Jennifer Jacobs, who have helped us a lot in the beginning of the tool design. We would like to thank all our collaborators, Mira, Will, and Danny, but not here today. Danny's not here today. Mira and Will's right there. We'd like to thank Adobe Support and NSF and our giant team of wonderful people. So come talk to us if you see us. And thank you. We'll take questions now.
Okay. Hi, I'm Nick Chen from Microsoft Research. I was wondering if in your tests with people, if you saw any instances where people's aesthetic vision conflicted with kind of the electrical constraints of the circuit, and what happened, how did people resolve those tensions?
So we saw that a lot, actually, because this is a very unfamiliar medium to people. Like, for example, people would want to create traces, and they were really mad that the red and black can't cross. Again, this is something that we want to create a tool so that people can explore how they can balance all these things, because even the balancing of how to route electronic circuits is a very difficult problem even for electrical engineers. And the fact that other people can come in and start thinking about different solutions to route these traces and solve the electrical problems that you just mentioned is very interesting to the broader community as well. But yeah.
Okay, maybe one very short question here in the front. First row. Sorry.
Very nice work. So I think a lot of the problems you mentioned are like this creative vision of people, and then there's this electrical engineering constraint. In electrical engineering, it's also the same problem. But have you guys thought about like layers? So engineers solve this through like stacks of layers, but then you just have like a via that crosses between the layers. So have you guys thought about that in like either in this iteration and maybe in future versions?
Yeah, so that's very interesting because I have a fabrication background. I'm a MEMS person, so there's so many different ways that you can solve multi-layer problems. And so that's definitely something that we want to incorporate in the tool in the future as well, is how people can stack different materials in order to create different properties like capacitive, even just dielectric and whatnot. But it's definitely in the future work.
All right, okay, let's thank the speakers again.